from Queensland University of Technology, and he's going to talk to us today about some old and new moving boundary problems for Hele-Shaw flow. So thanks, Scott.
Thank you, Linda. Before I start, I should say that this is joint work that's been probably mostly done by a student of mine, Morrow, who's just finishing up right now, and also Michael Dallaston, and my colleague Tim Moroney. And we are all at Queensland University of Technology in the city of Brisbane and in Australia, in other cases. Okay, so now, in case you don't know, or perhaps you need reminding, I'm going to talk about Hele-Shaw flow, so I'll tell you what a Hele-Shaw cell is. I'm just remembering I was going to put up a picture of my student Michael's Hele-Shaw cell, but I forgot to do that. A Hele-Shaw cell is an apparatus made up of two flat plates, most of the time flat plates held close together with viscous fluid sandwiched in between. So it's a viscous fluid sandwich. And really the situation that I'm interested in is when there are two fluids in between the plates. Let's say that they're immiscible fluids, so they don't mix, and that there's a sharp interface between the two. Then, in that case, when the less viscous fluid displaces the more viscous fluid, the interface between the two is unstable, and that's called the Saffman-Taylor instability. So, physicists are interested in the Saffman-Taylor instability because it leads to all sorts of tip splitting or branching structures and pattern formation at the interface. And here's an example of that. So here are some figures here, and what you've got is a top view of the Hele-Shaw cell. So imagine that you've got your two flat plates like this held close together, but someone is looking from the top, and that's what they're seeing here. And this dark pink must be the more viscous fluid, and this light pink must be the less viscous fluid that's been pumped in. Here you can kind of just see some sort of syringe or something that's being pumped into the cell, and as less viscous fluid is pumped in, the interface is kind of moving generally out, and because it's the less viscous fluid displacing the more viscous fluid, the interface is unstable and you're seeing this pattern formation. And here is a close-up of that. So these images are taken from this website, nervous system website. I think Rob McDonald might have mentioned this website during his seminar at the second workshop.
Why it's nervous?
I don't know, but I think maybe you might remember Rob mentioned that on this website, at least in the past, the woman who runs this makes jewellery and clothing and so on, all inspired by Laplacian growth and structures like this. It's actually quite interesting. Okay. So, okay, there's two parts to my seminar. I put slides together. I see there's 30 slides, and I know I can't do 30 slides in a minute, so I'll just truncate when my time's up. And that might be like 22 slides or 25 or something like that. Now, part one.
Okay, optimally then.
Optimally might be about now. Part one will be some old problems in Hele-Shaw flow, and part two might be some not so old problems. And here are some images actually just of interest here. These are exact solutions to a model that I'll talk about in a moment, and they're by Sam House, and you might just remember these images from one slide ago. They kind of look similar to that, so again, we'll be looking from the top onto the Hele-Shaw cell. Okay, so old Hele-Shaw problems, part one. Okay, so this is a problem in fluid mechanics, and the model that is normally applied is something like this. What happens is we assume Stokes flow between the two plates, so that's slow viscous flow. And if you take this slow viscous flow equations and average them over the gap, then you get something like this equation in the blue, which says that the velocity here, which I'm calling Q, goes like the negative gradient in the pressure. So this looks just like Darcy's law for saturated flow in a porous medium. And so this is another reason why some physicists might be interested in this apparatus, which is that it acts as a 2D analog for flow through a porous medium. And you can imagine that it's much easier to set up an experiment in a 2D Hele-Shaw cell and make some observations than what it is to do an experiment in a 3D porous medium that's totally saturated. Okay, this equation here is just continuity of mass, and together both of these give Laplace's equation for the pressure. So in the case of one point could be that complex analysis is good for problems that are governed by Laplace's equation. And this is in the flow field. So here at this point in the model, I'm just going to ignore the less viscous fluid. Let's just say that it's air. So here is a geometry. I'll mention three geometries. Here is one where the configuration is the same as that image that I put up before, the less viscous fluid being injected, say, through a syringe or something. At the interface, there are two conditions. One says that pressure is related to the curvature via surface tension, and this other kinematic condition just says that fluid doesn't pass through its own boundary. Okay, so for this particular model, there's an infinite amount of this fluid. Let's say it goes on infinitely far, and there's a far field condition, which is saying that we might be pumping fluid in, inviscid fluid in at some rate, but that's the same as extracting fluid out infinity at the same rate. It's hard to do that, so let's just imagine God is extracting fluid at infinity at that rate, and then you get this type of far field condition. Okay, so let me talk for a little bit about three different configurations that have been flogged to death in this area. One is like this one up here. So that's like the experiment that I described in the first slide, and is equivalent to the schematic that I just had a moment ago. So I'm looking from the top of my Hele-Shaw cell. I have some, you might imagine, sort of like a bubble of air where air has been injected into the thing here, or fluid is being extracted at infinity. But I can also just have a blob of fluid. I have a blob of fluid sandwiched between my two plates. In that case, I might say like to extract the fluid out of a point through a syringe, say. And then in that case, so if I'm extracting fluid out of here in the blob configuration, then I still have less viscous fluid displacing more viscous fluid, so the interface is still going to be unstable. Another one is, so I'm going to call the first one bubble, the next one blob, and the third one is a channel, where now I've got these two walls here on the top and the bottom. Remembering this is actually a top view, so the walls are like this, and you might be pumping air in from the left, or you might be extracting fluid out from the right. So let me just call that the channel geometry. And in that previous slide, I actually had dimensional equations, so now let's just make those dimensionless. And if I have phi as my velocity potential, then it's phi now that satisfies Laplace's equation in the fluid. So that here, that's the blue or the purple. So for the bubble problem, the fluid's here. For the blob problem, the fluid's here. For the channel problem, the fluid is to the right of the interface. So it's Laplace's equation in the fluid. This kinematic condition, which is the one that's just saying that the speed of the interface is given by the normal derivative of phi. That's to say that fluid doesn't pass through its own boundary. The dynamic condition relates in effect, this thing is like the negative pressure, relates the pressure to the curvature by surface tension. And then, well, there's one more condition, and it's different depending on which one of these configurations you choose. I already mentioned it. So there'll be a far field condition where Q might go like log of R, if you're extracting fluid out at infinity, or if you're sucking fluid out at a point here. For the second configuration, it also goes like log of R, or in this case, for the channel geometry, you might be extracting fluid out, so you get a constant speed in the far field. Okay, whatever, they're just some details, it doesn't really matter so much. Okay, what can you do with this problem? Well, you might say, in each of those three geometries, you can map from the unit disk to the fluid region. So I don't have a schematic here, so it's a bit tight on space. So imagine you have a unit disk. Now, so in a mapped plane, the fluid is inside the disk, and you map to the fluid region of interest. So in those for these three cases, you will have, say, a different behaviour as my mapped variable zeta goes to 0. So f might go like 1 on zeta for the bubble case, because you're in effect turning the thing inside out and mapping to a disk. In the second case, f just goes like zeta. In the third case, you get a log because you're taking a channel and in effect flipping it around. Now, I haven't included any detail here, but you can reformulate this problem as one of these equations here, which is the PG equation. So, in effect, what you do is you try to get that kinematic condition, which is saying that the normal velocity is equal to d phi dm. You can write down the normal velocity in terms of the map, and in effect, it kind of looks something like that. It's almost like that. So that's like the left-hand side of that condition, and the right-hand side is d phi dn. That comes from phi, which is the thing you're solving for. But once you map it into the disk, you're solving Laplace's equation just in the disk, and the solution is just like log of zeta, maybe plus another thing if there's surface tension. And so when you compute d phi dn, you end up getting something like this. I mean, there's some normalized norm. You've got normal vectors, and there's a bit of algebra. In effect, it looks like this. So the problem now is to find the map. What is the conformal map that maps the disk to the region of interest? And that map f must satisfy this equation. So we've got f, it's a function of zeta in t. The right-hand side is some q, which is related to the far field, like how much stuff you're pumping in or out, say. And this here is the surface tension here, and this is like the curvature. And this equation holds only on the circle. Okay, so this is a kind of a well-known equation. So I'll just talk about a couple of exact solutions to this problem. Now, for these exact solutions, we will neglect surface tension. So let's just say surface tension is 0. In that case, the PG equation just looks like this. So let's find some map that satisfies this equation. That should be on the circle. So that should be say, magnitude of zeta is equal to 1. Okay, for the blob problem, so if you're following me, this is the blob problem. So we're just sucking fluid out of a blob. Okay. For the blob problem, you want to find a mapping that satisfies this equation. Well, one way could be to look for a solution that is a function of time by zeta plus a function of time by zeta squared. And you just take that ansatz really and throw it back into this equation, and that gives you two equations for A of t and B of t, and you can solve them exactly. And what you find is that you get one way of writing the exact solution looks like this, but I wouldn't worry about that so much. You can find that you can show easily that there are critical points to the map. So when the derivative is equal to 0, and they're given by some exact expression, and this A of t is a function of time now that decreases to 0. So in effect, what happens is the interface looks like this. So this is like say it's like a near circular blob. You're sucking fluid out of that, and that it contracts. As it contracts, a bit of it sort of moves in faster than the rest. It's off center. It's not a circle where the fluid is extracted at the center. Just imagine this as being maybe a slightly off center extraction point, and then this little nodule starts to appear, and that turns into a cusp. So what's happening in the mapped plane is that critical point that I was talking about. It's 0 outside of the fluid, so here the fluid is inside the disk. That critical point is here, and as time evolves, it moves towards the disk. So it touches the unit disk in finite time, and that's precisely the time that a cusp forms on the interface. And you can do all that by hand, and I'm pretty sure that this is due to Baranova-Kachina in 1945, but my Russian is not so great, so I can't really read the detail. Okay, so that is a summary of that exact solution. So now let me put up a summary of by schematic of a couple of other exact solutions, just by example. Here is an example in a channel. So if you remember, you've got this channel, and there's air, so injected at one side, or fluid injected at the other end. There's an interface moving from left to right. If you look for a solution that satisfies this type of ansatz, again, you've got these two unknowns, A of t and B of t. You can just plug them into this equation. It turns out that it all works out very nicely, and you can write down an exact solution. And so the interface, which was almost flat at the beginning, developed some sort of perturbation that grows and then turns into a cusp in finite time. So here in the map,
So I'm going to express a solution for A and B or just some ODE?
exact explicit expressions for A, in this case B. I might have written down, I didn't quite write them down, but here, for example, there's two equations here. You could say solve for A or B, put it into the other
It's
one.
not even ODE,
It's just an algebraic equation,
They're going to be solving ODEs.
Sorry?
But you solve an ODE to get them.
Yeah, so the ODE is very nice. It integrates once. Okay, so in this case, this is my map plane again. So imagine there's some critical point where the derivative of the map is 0 over here, and as time evolves, that critical point just moves and touches the disk. It's on finite time. And when it touches the disk, it's precisely the same time that the cusp develops. Another example is where the ansatz looks like this with a log. And what happens then is that the interface develops into a kind of a nice finger. So if people know anything about Saffman-Taylor fingers, they kind of look like that. And for this exact solution, there is no cusp at finite time. So what's happening is, I'm trying to remember, okay, that you'd get, again, critical points of the map that are here, I think in pink and moving to the left, and they want to head towards the disk. Remember, if they hit the disk, then there'll be some finite time blow up. But there's also singularities of the log term. There's a singularity in the log term, and they're located where the grey points are. Actually, they're on the other side of the circle, but putting that aside, they also move towards the circle, and you can show that they are always closer than the critical points. They don't reach the circle, so they kind of block the critical points from ever touching the circle. Okay, now very quickly, now let's move to the bubble configuration. This is now if I've got air. This is the same as the very first slide, where you can pump a less viscous fluid into a more viscous fluid through a point. And so here you get interfaces that are moving out and moving out. If you look for an ansatz like this, A of t over zeta plus b of t divided zeta to the n, here n is 6, you can, again, solve for A and B. Get these exact solutions. Again, they're critical points. They move from out here and they touch the disk at finite time. The moment they do that, you get a cusp. And here's another example where you don't get a cusp because you get these other singularities of the log, and they kind of act to block the fixed points from ever touching the disk. So these are old problems because, for example, these are in Howson, Ockenden and Lacey from 1985, and these are in Sam Howson's paper in 1986, so this sort of stuff is quite old and very well known. Okay, now what if you add surface tension? So you can, if you like, still try to solve those problems with surface tension numerically using that formulation. The PG equation just looks more complicated. I put it up there before. You can do that, but I think that it's probably not a very good approach to solving the problem numerically, and there's probably a number of better approaches. So this is one, and this is due to Liam. It's his level set method. So this is the problem where you're injecting air, like on the first slide, you inject air into the cell that has fluid viscous fluid in it, and the interface is moving out. And so here are 4 of these examples, and you can see lots of things. For example, you see the finger formation. You can see that there is tip splitting. So what's the difference here? Here you have higher surface tension and lower and lowest surface tension. The lower the surface tension is, the more tip splitting and branching you get, and you get other things which are labelled. So here's some tip splitting here at number 1. Here at 2, sometimes fingers start to grow, but they kind of get blocked off, and so they head back in like a snail. This thing here looks like feathering, where there's some sort of fingering on the side of a larger finger. So these particular simulations were done by my student Liam, but you see other very similar simulations that have been done in the past, and some better known papers are like these from, say, even 1994 to 2007. So again, this is rather old. Okay, so now just to finish off this part with a couple more examples. I did have that blob problem before. You might remember these exact solutions, for example, where you've got a blob without surface tension, you extract fluid out of the blob, and then a cusp forms at finite time. But when you add surface tension, again, the cusp doesn't form. Instead, you end up sucking all the fluid into a point. So this is a numerical solutions to indicate what's going on there. Here, there's an initial condition that's a circle and it's off center, and this happens. Or you could have an initial condition that's like a circle but with some perturbations. Here, it just happens that there are like -3, 7, 15, and 25 low perturbations on the circle, and it goes like something like this. And what typically happens is that one of these fingers that are growing in now seems to start beating the other ones in, and then it moves very quickly and moves into the center. Another observation is that there's not so much tip splitting, or sometimes none at all, for this blob problem. And so the last one of these examples is the channel problem that I've spoken a bit about. If you remember, here are some numerical examples for the channel problem. What they are is just an almost flat interface at the beginning, and that interface is unstable. If you remember, it evolves into a finger-like shape. So here's like a finger starting to develop. In the top case, the surface tension is quite small, and the two fingers split into two. So the one finger splits into two. Here, surface tension is increasing as I move down. And if you know anything about the Saffman-Taylor finger problem, you'll recognise that this thing is going to develop into a very long finger, and that its width is related to the surface tension. Again, people are computing these sorts of things numerically, for example, from 1986. So again, this is an old problem. Okay, so that's part one. So you sort of test yourself to see if you're still awake or asleep. If you're asleep, then you can stretch. Part two is coming. Okay. So now I've got a warning, which is there's no more complex variable methods, I'm afraid, in the talk.
We all live in.
I should have confessed earlier, but then maybe even few of you would have come.
Please, that was joke. You don't have to leave.
Up to you.
Okay. So what is part two about? Okay, I'll just start off this in part two just to again just mention that my student Liam has developed this code to solve these problems using a level set method that I won't describe in any detail. And here are some examples of some experiments in this case. These are old experiments done by Chen, and here these are different flow rates, low, medium and high flow rate, I think. And so one point here is that Liam has used the same parameter values as in his experiments, just to copy them over from the paper, and proof by eye is that these numerical simulations are doing a good job of reproducing the experiments. Really what I want to talk about in part two is that, first I'll just say that more recently what people are doing experimentally is to change that configuration, the more traditional configuration in a Hele-Shaw cell somehow, in an attempt to maybe control or suppress the viscous fingering patterns. So you might imagine in some applications the viscous fingering could be considered to be bad. Say if you're trying to maybe displace oil with water under the ground or something like that, you might want to suppress the fingering or control the fingering. And that's some very loose motivation for doing this. So now with that in mind, a very crude way of trying to reduce the fingering pattern could be just to reduce the flow rate. So I just mentioned before that these are the same experiments by Chen. This is, I think, injecting the same amount of fluid from A and B, or left and right, but just at a different flow rate. And the fingering pattern is more harsh here. There's more tip splitting and branching than there is here. So a crude way to, say, suppress the fingering could be just to decrease the flow rate. But people are doing all sorts of other things. So for example, Amy Tsai from University of Alberta has taken the top plate, and instead of having a parallel plate, tapered the plate, so it's coming out at some angle. And so here on the left is a normal traditional Hele-Shaw cell with parallel plates, and that's the same type of image that I've been showing a number of times in this talk. And on the right, she's got tapered plates, and the flow rate is such that she's able to completely suppress the fingering. Another example of trying to control the fingering is here in the orange. This guy is Zhong Zhang, who I think is here in Cambridge, but he was in Howard Stone's lab at Princeton, and he is in these two cases here attempting to pull plates apart at a certain rate. So they're normally fixed at a fixed distance. He's pulling them apart at some special rate in an attempt to
Be the time-dependent
rate, something like b to the 1 on 7 or something. So in an attempt to fix the number of fingers. So this is some strategy to control the number of fingers that you get in. Remember, typically you get tip splitting, so the number of fingers increases as you go.
So this person, he's where? In math or in which department?
He's in damned. But he
So we can visit him in the lab.
I think you
serious.
can, but I have not seen him once since I've been here. He's hiding somewhere. Okay, I'll just sort of mention, I'm not going to talk about this one, but people are also, they're doing all sorts of things more recently. One is to replace the top plate with an elastic membrane. And when you do that, you can say, so here there's no elastic membrane. This is in Anne Jules' lab in University of Manchester. And in this case, there's an elastic membrane where the fingering pattern has been completely suppressed. This third case is interesting. The fingering pattern looks kind of different with stubby fingers. I might just refer to that one more time later, if I can fit it in my hour. Okay, so what I'm going to do is talk about, in the second part, is talk about some of these strategies for controlling or minimising viscous fingering, and demonstrate how Liam's numerical scheme can be used to simulate these, or maybe to suggest alternatives. Okay. Okay, so now to do this, you may or may not remember this model for a Hele-Shaw cell that I put up before. This is the same slide, except I've just made an adjustment. What if we allow the plates to be not parallel, but at an angle alpha? Okay, so that's going to change the model a bit. Or what if I want to allow for the plates to be pulled apart at some time-dependent rate? And I'm still going to inject at some flow rate q. So in that case, the model is slightly different to before. I still get this Darcy law governing equation, but my conservation of mass looks different. And people might recognise this. It's like you get this sort of equation from a lubrication model. And now it's kind of important to, this is my pressure condition or dynamic condition that relates pressure to surface tension. Now there is a curvature from the top, but there's also a curvature you get from the side. And that's more important now because the height that you get, the B that you get, which is the distance between the plates, is now spatially dependent or time dependent. Okay, again, the fluid can't pass through its own boundary, and you need some sort of vacuum condition that matches. That in effect says how much fluid is being extracted. Okay, so normally if I was talking about this type of problem, the first thing I'd do would be to talk about linear stability, because it's the most elementary technique that you can use to try to understand what's going on. But in part, I did the second part first, and also I forgot to put up a slide at the beginning about linear stability.
So I've just got a quick question. So on that previous slide, you had sort of you've also got the curvature in the plane of the cell, which people don't always include. So in problems like this, does that turn out to be important?
Yes, this term here is now important, and normally it's a constant.
Yeah.
So when it's a constant, you absorb it into your pressure. But now, just imagine that there's a small change in B due to this. I'm going to say that alpha is small. But even if B changes by a small amount, the 1 on B is the difference between 1 on B before and after.
So you have to be on.
So it does have quite a significant effect.
Have to be on two right figures. which of these B's here in pressure?
Okay, I have two what?
You have two B, you have two figures on the right? You have one B of R, B of T.
Yeah, yeah. Oh, okay.
Which B is in equation?
It's either. So I'm not going to taper and pull them apart at the same time. I could. I either decide I'm going to taper them, in which case it's B of R, or I'm going to pull them apart.
It could be both.
Could be
But
both,
it's
yeah.
the same boundary.
It's the same model, yeah. That's right. Okay, what do I talk about? Talk about linear stability. So this is the case where we've got, say, almost a circular bubble of air. You're pumping air into that, and this almost circular interface is expanding out. So what would make sense would be to solve for the problem where the interface is precisely a circle, because you can do that with pen and paper, and then you perturb that and try to track how fast the modes are growing or decaying. So, okay, so for a different reason now, all of this is now back in dimensional quantities, in case anyone's following, and that's because Liam was keen to compare with the experiments. We just wanted to look at dimensional variables. So back to P being my dependent variable. Okay, so it was 5 before, now it's back to P. Okay, so how does linear stability work? It works that there'd be a leading order solution, which is the solution for a circle. You get some pressure, and let's just say that the interface is given by R as S of theta and T. Okay, this is the interface that's expanding out. So it depends on theta and T. But for the circular case, when the interface is a circle, it doesn't depend on theta at all. Okay, the radius just depends on time. So I can solve for that term and that term exactly, and then what I do is I add on a perturbation like this. So for example here, I have my S, which is the location of the interface, being the radius of the circular solution, the leading order bit, plus some small number epsilon by some gamma n by cos n theta. So I'm interested for each n, each mode n, how fast the gamma n's grow or decay. So you can work out that the speed of the interface for the circular solution is related to the flow rate at infinity. And so the faster you suck fluid out at infinity, the faster the interface moves. And that the growth rate of each perturbation is given by this expression here. So there's a lot of stuff in here, but all you really want to see is that the faster the interface moves, the faster you extract fluid at infinity, the more unstable each mode is, because it's a positive term. And here surface tension is just there. So the higher surface tension is, the less unstable a mode will be, or if it's already stable, then the more stable it will be. This sort of thing was done, again, a long time ago by Lincoln Patterson, for example. Okay, so something that I want to talk about, if I have time, is to say that the context here is, what if you could try to change one of the features of this traditional experiment, and you want to control, suppress the fingering instabilities? Well, if you want to, say, suppress the fingering, then one option is just to change the flow rate. And okay, it's been suggested in this paper by Jose Miranda and colleagues that you can, if you were to pump in not as a constant but as a linear rate in time, so this is your flow rate, it's slower at the beginning and then faster at the end, then you should in some sense suppress the fingering. So this is an idea, and the idea really is that you're trying to set up a fair test. So this crude method I suggested before, where I just change the flow rate to try to reduce the fingering, that's not very exciting at all. A better test is to say you're going to pump in the same amount of fluid over the same period of time, and then you want to change the flow rate. So what's the optimal way of designing a time-dependent flow rate to suppress the fingering if I want to inject the same amount of fluid, or say extract at infinity the same amount of fluid over the same period of time? So I'm not really going to say where they get that from, but I'll just suggest that this is okay. So I'm up to slide 13, and I'll get more than halfway before my hour's up. Okay, so now what about these other strategies? What about minimising growth of viscous fingering with some of these other strategies, the ones I mentioned before? So here, what about tapering the plates? So I mentioned before that And there have been experiments where they replace the top plate, a flat plate, with a tapered plate. And the idea is to suppress the fingering in some way. Okay, well, if you do that, you might want to write down linear stability for that problem. Well, this slide is the same as the other slide. I copied and pasted the details, and I used the same LaTeX file, LaTeX for each. The difference is that when you taper the plates, you get an extra term here in the Morrow. Okay, so the growth rate of each mode is the same as what it is for the traditional problem, minus some other term. So provided this thing here is positive, and this is your angle, then you can see that each mode is less unstable than what it is before. Now there's more detail in here, I'm not going to talk about. This sort of thing has been done in a number of experiments, for example by Howard Stone, again in his lab. Now, for this case, with tapered plates, if you want to inject the same amount of fluid over the same period of time, and you're allowing for the top plate to be tapered, then by following the same method as with this previous paper that I haven't actually summarised, but you can derive a nonlinear ODE for, in effect, the flow rate Q. So here I'm just...
So it's again, what's different with red terms from black?
Okay, so the black terms are the ones that were on the previous slide, just for
Yeah.
parallel plates. Okay, so if you've got a normal Hele-Shaw cell that normally has parallel plates, this is what linear stability looks like. Okay, so I just want you to think that whatever that is, it's what it was before. When you taper the plates, you add on an extra term. Okay, so tapering the plates has the effect of adding an additional term onto the linear stability analysis, or the growth rate of this gamma n.
I mean, I thought tapering means there is non-zero B, or not necessary.
Tapering means that if I look at my schematic, that there's
Yeah,
some
there is a
angle.
B here, right?
So B is going to be what it is here plus a linear bit in alpha.
But I mean, in black terms you also had B, not only the red one. This is confusing me.
It's just constant B in the black terms.
Okay, so what the truth is that when I slipped this past you, which is that there's more detail here than I want to talk about, is that this term here is also changed by having tapered plates. So you're not meant to pick up on this. Okay, so what really happens is that I also said that provided this term is positive here, then it has the effect of making each mode less unstable. But it's more complicated than that because there is a term in here that changes with as the interface moves out, its location has a different, it's associated with a different B, and also that this term here is not so straightforward, it's not just always positive. So there's more detail there, given the time, and I'm not going to go into it. So there's probably three competing influences actually in this term. Okay, so maybe I will just, I'm going to go on to, I'm going to skip that. So here is just say, if I have to inject a certain amount of fluid over a certain period of time, then, and there's some average flow rate, whatever it is. Okay, so here I'm comparing four different strategies. The first one is to inject some fluid over some fixed period of time at a constant injection rate and in a traditional Hele-Shaw cell with parallel plates. Here I've got that linear injection, so I'm changing the time dependence of the injection rate in an attempt to, say, suppress some of the fingering. Here I'm tapering the plates, but with constant injection. Here I'm tapering the plates with some optimal injection. And now by eye, it looks like as you go down the column that the fingering has been, say, suppressed in some way. Also,
These are numerical computations, right?
these are all numerical computations. Okay, so I just say by eye that
Optimal means suppress fingering as much as possible.
optimal means optimal in a way that I haven't mentioned, which is to solve some optimization problem related to the linear stability problem. But it's probably a couple of slides. So. You look for the most unstable mode, which you can solve by hand. You plug it in, you get a growth rate at that most unstable mode, which is a time-dependent thing. Say, let it be a real number. And then you have a growth rate over the whole time. You integrate that growth rate, and then you've got some interval that you want to minimise. That's a summary of that.
So yeah, I was just following up on Pavel's thing. So you're optimizing for sort of minimum instability in some
Yes,
sense.
in some sense. Okay, now this is just by eye. Another sense is just, well, as another measure. Okay, I like just saying by eye. This looks like it's doing a good job, but we can measure, say, how far away from a circle an interface is a number of different ways. There are lots of options. One is this isoperimetric ratio, which you may have heard of. This thing is L squared over 4 pi a, where L is the perimeter. So when you have a circle, that's 1. And the further away it is from a circle, the higher that number is. Okay. And so this here, the blue one, is for that, is for this example here. So as time increases, this measure of how far away from a circle the interface is increasing. And then in the second case, that's the red one. The third one is this yellow one, and the fourth one is the green one. So here's some more quantitative measure about how suppressed the fingering is. Okay, I'm just going to skip that out. And that, in case anyone was paying attention, I did mention before that there were some stubby fingers that appear in that experiment with an elastic membrane on the top. So if you replace the top plate by an elastic membrane, you can observe these stubby fingers that don't look at all like normal fingers, say, like these ones. But you do get them here, and that's probably because when you taper plates, you've got tapered plates that locally near the interface, it looks like the situation you get with an elastic membrane, where the elastic membrane is also deformed as the interface moves under it. Okay, so that's still a little bit of time. Okay, so now maybe let's just say, just for fun, what if we rotated the plates? If you have rotating plates, you can inject in, so the whole thing is rotating, a rotating cell, and so you're still injecting fluid into the cell. Then you can write down linear stability for that problem, and the details, like all of this, is the same as before, so this is the same text as before. And here are the growth rates of each perturbation, and they look like they do before, except that there's another term added on. So what that means is that if you're rotating at some rate, the faster you rotate the whole cell, the more stable or the less unstable each mode is.
Is that the centripetal effect or the Coriolis effect?
It's the first one. So
It comes in before the Coriolis.
will be ignored.
Yeah, just ignore this.
So, in fact, after some time, it appears that all of the modes become stable. You can play the same game and imagine that you're injecting the same amount of fluid over the same period of time and follow the same analysis that I didn't summarise. You can drive an ODE that you can solve exactly and try to predict what flow rate would be the best one possible to do this. So the top row is injecting some fluid but then rotating at a higher and higher rotation rate, and you can kind of see here that fingers start to develop but then they retract. So here fingers start to develop and they retract. So in this particular example, you're rotating fast enough that all of the fingers are suppressed and you end up with a circular interface. Or if you inject at this, what I'm going to call an optimal injection rate, then you can suppress them for a lower injection rate. So here is this isoperimetric ratio, which is a measure of how far away your interface is from a circle, if you remember, 1 being a circle. So here's 1, somewhere down there, and that these are these different, so let's say these different cases across the top there. So that's the first, second, third, fourth, and fifth. And so for most of these, this isoperimetric ratio increases, reaches a maximum, and then heads back down to 1 as the interface heads out towards a circle. And something similar happens for the second case.
What are the sort of bluish bands along the curves in the left figure?
Bluish bands. Oh, yes. Okay. So the initial condition here is a circle with a random combination of modes added and a random phase shift, because if you were to actually start with a circle, it would stay a circle. Instead of just doing that once, we did it, I think, 10,
Some kind of
10
measure of
10
uncertainty.
times. That's right. So we did it 10 times, and then we've got sort of plus or minus standard deviations.
But your noise amplitude is always the same.
Yes. For each of these, the amplitude is always the same. Okay, so my watch. So I mentioned before there were orange experiments, the experiments done by Zhang, where he is trying to pull plates apart at a special rate to control the number of fingers. So normally there's tip splitting, fingers split into 2 fingers and then they split into 2 and so on. But what if you wanted to control the number of fingers? So now imagine I've got plates, they're lifting apart. I want to write down linear stability for that. Well, the details are the same. So here, this is the same detail as before. This is my growth rate of each mode, same as before, except I've got some extra term on the end. So again, the linear stability for this problem looks very similar, and you can get a lot from that. So what if I now try to, say, use this formula to calculate the most unstable mode, and then try to fix that most unstable mode. So one way to do that is to inject at some rate, let's just say you don't know what it is, at some power law, and pull the plates apart at some power law, and try to solve for these two, say these two numbers, alpha q and alpha b. If you do that, then some special combination of the two are such that the most unstable mode turns out to be a constant. Okay, so this is a game that you can play with pen and paper. It's the same game that Zhang did, and then what he did was fixed q to be a constant, and actually tried to do it with the experiments, and you get b to the 1 on 7, I think. So that's where he got this idea from. So here what we've done is, like, these are Zhang's experiments where this is some control parameter. It's just some fixed number, and that if you increase that control parameter, you should be able to try to increase the number of fingers that you get in the experiment, in this case, or in the simulation, in this case, in at least second and third cases, and that you can predict what that fixed number of fingers is. So here this is from Zhang's paper, where he's predicted the number of fingers you should get, and this is this control parameter J, and here we've done some simulations where we're predicting the number of fingers we should get, and this is the control parameter J, and what you get in reality, again, there's some dot with a plus or minus standard deviation, because we've got random combinations of modes as our initial condition. You actually get something which is slightly less than this prediction. So the number of fingers you get according to this prediction, which comes from linear theory, is almost the same, but not quite the same. And really the reason for that is that sometimes fingers start to develop, but then they kind of get pushed back in again by they get out-competed in a non-linear way by their neighbours. Okay, so this is Liam simulations, and this is the one where you pull the plates apart with b to the 1 on 7. Here is if you inject at some special rate, which is t to the minus 1 on 3, which is already well known in the past. And you can also do combinations of these, but I haven't shown you those results. Okay, so I'm running out of time here. So I'll just start to flick through here. So just another idea is that you can have two interfaces, one in the inner interface and the outer interface, like in this experiment, Ward and White, and like in the simulation. So normally in the lab, you don't have an infinite amount of fluid going on forever. You have a finite amount of fluid, and when you inject into say you're injecting air through that point, the inner interface is the one that's unstable because you've got less viscous fluid displacing in more viscous fluid. But the outer interface is at least nominally stable because it's a more viscous fluid displacing less viscous fluid, but it also does get affected by the inner interface. And then at some point, the inner interface will reach the outer one, and there'll be some bursting change in topology. So this is an interesting problem. I'll just say that, and I'll just say that we did some time ago. My former student Michael Dallaston and I wrote down some exact solutions for this problem. Actually, Darren showed me how to do this one time when he came to visit QUT, and then Michael worked out all the detail. We do have numerical simulations of this. I mean, what happens is that when the pressure difference, this is driven by a pressure difference between the two interfaces, and when you increase the pressure difference, you increase the number of fingers that you get in a way that's not surprising. Okay, we have contracting bubbles with two interfaces, and we had ones that were rotating around. But I'll probably wrap it up there. Okay, so in summary, so the first point is that for a normal Hele-Shaw cell with parallel plates that are held at a fixed distance apart, you can use complex variable methods to reformulate the problem in terms of a conformal map. And then for the case where you neglect surface tension, you could write down some exact solutions. I've put up a few examples. There are many other examples that have been, and when I say written down, in this case you can kind of write them down, but in other cases they're more complicated. Typically these solutions lead to some sort of finite time blow up in the form of a cusp, but sometimes they don't. I mean, it depends on some of the detail, but when you add surface tension to the model, either solving the problem numerically with your conformal map or using a completely different method like we've done here, then this type of finite time blow-up is regularized by the surface tension. So here we've got numerical simulations using the level set method, and that's similar to what's been done in the past. Then in the second part, I tried to suggest that more recently people are altering the Hele-Shaw cell in a number of ways, and I've just mentioned a few here. And one of the things that people are trying to do is control instabilities. If you look up controlling instabilities in Hele-Shaw flow, there's heaps of papers these days. And so two of the ones that I've mentioned were to taper the plates, and the other one was to lift the plates apart. It's a time-dependent way. And so an idea is that if you're doing that, you can also inject it in a time-dependent way to suppress fingering, and you can try to, by pen and paper, work out what could be the optimal way of doing that. And we're doing this in a way that we're calling a fair test, which is to inject the same amount of fluid over the same period of time. The other thing I was talking about here is that you might want to control the number of fingers you get by injecting in a certain way or pulling plates apart in a certain way. And finally, I did mention doubly connected flows, but I'll skip through that. Okay, so just to say that some of this work is partly funded by the Australian Research Council. I'm very grateful for the Institute for having me here during this period of time, and also the Simons Foundation. And part of this work at the end is published in this paper in JFM this year. I'm not sure if anyone's really interested, but that's my Twitter handle, and that is it.
Well, if you have time, a couple of questions. First question, just for a better picture to understand. So this guy Jean, right? So I don't know. So he basically, if I understand you correctly, it was competition between Princeton and Cambridge to hire this person. What is that some important motivation in the applications? Why this problem? Why he was so hot on the market?
Okay, well, I
she,
certainly can't comment on how hot on the market.
No, but I mean, is that this a problem important for some applications with choice of thinking, or it's more like just fun problem?
Okay, well, yeah, so that's a very different question too.
Well, it's related.
I don't know if it's related. Look, at this level, it is. It seems like it's more of a game, but collectively, there is lots of activity in interfacial flows, and Hele-Shaw flows is just one part of that, in trying to do all sorts of things to control the instabilities. So I think broadly it's an important issue, but at this level, it's I think it's interesting from a mathematical perspective that you can, well, I didn't talk about here, but you can in effect derive self-similar problems where you're fixing the number of fingers. Why Zhong Zhang did it in the first place, I can't tell you that, but in fact he did more than this. He let everything be variable. He said, imagine if your viscosity was time dependent, imagine if your surface tension was time dependent.
Is it linked to microfluidics? That's a pretty hot engineering topic, isn't
Microfluidics is a hot engineering topic.
it? Is it related in any way?
Well, Hele-Shaw cells are like, narrow gapped devices. There's lots of those in microfluidics, but fingering is not such a problem because of the length scales.
I see.
So, okay, I'm not sure how well I answered that. The second of your questions.
Second, okay.
No, the second part of your first question. The first part I can't answer.
No, I think I had only one question so far. Second question, basically with selection of most unstable mode. I assume it will be regimes when it will be no unstable modes, or it always will be some unstable mode. I mean, because you have many terms, you can immediately see.
Okay, well, I didn't quite catch that, but
So you have some unstable transverse modes, right, with n.
yes,
Some stable, some are not.
yes. A wave number and how the growth rate will go up and then down in the usual.
Yeah, but basically there is a selection of this angular wave number, whatever we call it, n. Is there a regime where for all n it's stable, no instability? Or
Is
it's
that,
always,
yeah, if you inject at a very low,
so you need to
very
inject
low
very
flow
low.
rate. So that I'm calling an unfair test. It's not very exciting to say I can suppress all the fingers by injecting them so slowly that you have to come back in a week.
But otherwise no way to fully stabilize, only to have slow rate. No other way to fully stabilize except very low rate.
For the parallel pipe case, to fully stabilize, in effect doing that with a dimensionless number, I think the answer is yes, that's right.
So the control formulation was based on the linearized model,
Yes, that's right.
basically trying to keep the unstable eigenvalues under control. Has anybody ever looked at trying to control or optimize a fully nonlinear problem?
Yeah, well, I don't think so, but the guys that do this is with the linear model, but they also have a weakly nonlinear model that they like to apply to all of these configurations and more. So I don't know the answer, but I imagine that they've probably thought about applying this idea to the weakly nonlinear model. So and they're writing lots of papers, so it's possible, but I haven't seen it. Or I don't
Would there
know.
be any interest in solving a
Well, you
control
see,
problem for?
one of the interesting features is that it works at all, because
I agree.
you know, as you know, you're just perturbing the circle and you're getting some very small time results in effect until the fingers start to develop, and from then you might imagine that it's all inappropriate. So it does work well. Whether you get any more out of weakly nonlinear, I don't know. So I mean, a related point is that when you're predicting the number of fingers you get and you're trying to fix the number of fingers, you're doing that from linear stability analysis as well. And really, on the face of it, there's no reason why that prediction from linear theory on its own should work for fingers that are non-linear. But you do get a similar type of prediction using.
Because in principle, one could hit the problem of the machinery of the PD optimization.
You could, but then you might also run into Pavel's problem, which is that if you're working very hard to solve a problem, you want it to be very well motivated. If it's just a toy, then you might be seen to be wasting your good energy there.
Staying with the toys theme, would there be any interest in switching the rules of the fluids, injecting viscous into a non-viscous?
Yeah, so if you inject the viscous fluid into less viscous fluid, then the interface is stable, so nothing interesting happens. But, okay, it's not quite what you asked, but if you extract less viscous fluid from a more viscous fluid, again the interface is stable, so it seems not as interesting. But then you have, like, say, an interface that's shrinking to a point, and that's singular as well, and as the curvature blows up, and these types of problems are interesting from a mathematical perspective. It's not this instability that makes them interesting, it's more
The singularity.
A lot of your numerical results look remarkably similar to the experimental results.
well, that's
that
because
showed
we traced the
some.
experiment.
So they were not exactly the same, but they had the tip splitting in the right place, and so I just wanted to know how hard you had to work at that, or whether it was generic.
Well, not as hard as what you might imagine, but also, to be fair, imagine that you're a student and you've run it, say, 15 times, and one of them looks pretty darn close to the experiment. Which one do you choose? So, no, not really.
So you didn't run it back.
you know what you can do? We've got this degree of freedom of rotating the results around. So you don't have to work as hard as what you imagine. If you start rotating them around, then it just looks like this experiment.
I think the answer is you present one that looks just like the experiment and one that looks a little bit not like the experiment, so you appear to be honest.
Yeah, that's true. I mean, in one of these cases, so these are doubly connected cases. And see, like one of these is always, once it starts to win it, and then I think I had a blob case, say here, see this one here is, they're going in, it's winning. Well, in that case, if this happens, which, once one starts to win, then the pressure difference is much higher there and it moves faster. You get something like this. Then what you're going to do is rotate your result around to match the experiment, and all of a sudden it looks the same. So, yeah, I think that's
Well, if there's no further questions, let's thank